Doing $44 billion. That's a lot of money. That's a lot of money for Twitter. We'll see what happens. Yeah. I don't know. I guess it's worth that much. I don't know. I guess it generates money. I don't know. Anyway, we'll see. Hey, we're starting chapter 6. Chapter 6 is the last chapter that we're going to cover this year. Oh, I didn't know y'all would clap for that. I thought y'all would be like, oh, but you seem excited. There's 22 days of shul left, and we're going to spend most of them in chapter 6. Chapter 6 is my absolute favorite chapter of the entire year. In fact, I don't know why I don't just start with chapter 6 next year. I know, I like math. But this one is for real my favorite, because we're going to be learning about ways of thinking. Okay, we're going to be learning how to wend our way through a wilderness where no path has been made prior, and we have our mathematical machete, which is our pen, and we can make our own path, right? And sometimes the path that we go down, we're not committed to, right? And we can back up and try another path, right? So we might find ourselves like we're going down, and then there's a giant cliff, and we're like, oh, well, I guess I can't turn around, and you jump off the cliff, right? And then because you do it, your friends do it, right? No, you're like, oh, there's a cliff there. Let me just back up, and then we'll go down. We'll follow the river down a little bit. You know, we don't want to jump, right? Or, hey, there's a giant snake in the path. What are we going to do? Yeah, well, we don't have guns, but we'll get our machete, and we'll utilize it. We'll harvest it for food, and we'll use its skin as a bladder into which we can urinate if we're dehydrated, tie it off and carry it around our back so that we can drink our own urine if we were. Bear Grylls. Have y'all seen that episode? If you haven't seen that episode, Bear Grylls does that. No kidding. Yeah, it's out there. Vance is not impressed. Bear Grylls peed in a snakeskin, tied it in a knot, carried it around for a while, and then drank it later in the show. We're not going to necessarily do that, but we may make a nice belt or hat band out of the snake. We want to use every part of the snake, okay? And at the end, we're going to feel so accomplished. We're going to feel so much better that we found our way. We fought our way with a little sisu from start to finish, and we didn't just follow the royal road to the finish line, because there is none. There is none. Okay, that's what chapter 6 is about. And what do I mean by all that? What's the analogy? Well, I'm not really good at analogies, but anyway, or is it more of an allegory? Is it a metaphor? Simile, like or as? I know that. An allegory. An allegory. There you go. I like it. Okay, we're going to be doing proofs. We're going to be doing proofs. And if you go higher up in mathematics, the numbers start to become fewer and fewer in the subjects that you study as you go higher and higher. There's fewer and fewer numbers, and there's more and more symbols, because that's kind of what mathematicians do. They look for patterns, they try to make generalizations, and then they try to prove those generalizations. Those are called theorems. And that's kind of what mathematics does. And sometimes those theorems don't really have any practical applications, but years later, some people like John Nash, the economist, may latch on to a theorem that was proven, and it perfectly describes game theory, and he wins the Nobel Prize for it. So anyway, math is kind of like that. We're decoding the universe, but we're going to be thinking a lot in this section. We're going to be thinking a lot in this section. And that's the best benefit you can get out of this class, because you're probably not going to leave this class and do trig proofs ever again. You might, I don't know. Right? But you're going to be able to think. You're going to develop some habits of mind here, and you're going to develop a little bit of fortitude, and you're going to be able to persist. All right? Never surrender. Never surrender. Right? Unless the terms of surrender are favorable. Okay. Right. So anyway, here's what you're going to need to do. And I'm going to tell you in the very beginning. You're going to have to memorize a few things. You'll have room in your hard drive upstairs. Okay. You're going to need some RAM, and you're going to need some hard drive space. You're going to need both. The hard drive space is where you're going to store the identities that I'm going to tell you about. We're going to derive them. We're going to prove them. We're going to use them, but you got to memorize them. Okay. Those are like the tools of the trade. Okay. Then you got to have RAM because you got to be able to think quickly. You got to be able to think fast and efficiently and multitask and think of strategies, before you actually could do it, right? You don't have to jump off a cliff to say, oh, I should not have had jumped, right? You're like, oh, if I kept going, I will fall, and that's not good, right? So you can actually do this in your head. All you're going to be doing essentially in chapter 6 is you're going to be doing some trigonometric replacements. You're going to replace one thing with something that it's equal to. And then you're going to do a little bit of math. And then you're going to replace something with something that it's equal to, and you're going to do a little math. And all the while you're transforming something from a start to a finish. And you're going to have a goal. You're going to have a target that you're going to want to hit. Okay. And the way that you do that is essentially you have your identities memorized, and then you know what the math skills are. And we've been practicing those math skills all year long, like lick them over lick them, right? Remember that? Lick them over lick them? Nope. Remember multiplying by the conjugate over the conjugate? Remember doing that? Yeah, we're going to be doing a bunch of that, okay? So let's go ahead and start 6.1. Any comments or questions before we start? Happy birthday, Lizzo. Nah, don't clap for that. Yeah, don't clap for that. Anyway. Have you seen Harry Styles' version of Juice? Whatever. It's really good. Yeah. I heard his version before I heard Lizzo's, and then Lizzo sing it, and I'm like, can Harry just sing it from now on? I don't know. When you hear a song, a cover song, but you hear the second version of it, then you're like the first version that was so popular. You're like, no, that's not the way I learned it, right? True that, right? Okay. So here we go. We're going to look at types of equations. I'm frozen. There are several types of equations. Now, first of all, what is an equation? An equation is basically a sentence. It's a mathematical sentence. The verb is, and we represent that verb with a what? Equal sign, right? An equal sign. And you have an expression on the left and you have an expression on the right. And when you put the equal sign between them, you say this is that. Equality is very important in mathematics, very important. If you ever use the equal sign, you better make sure that what you put on the other side of the equal sign is the exact same or equivalent to the one on the other side, because if not, you are lying. You're lying. If you say this equals that and it doesn't equal that, you're lying. It's called mathematical prevarication, and it's a crime. Raise your hand if you like lying. Liars, right? Right, you keep your hand down because you like lying. I like lying. Lion King. There you go. Lying King. There you go. That's right. You all have some pretty good ideas in here. Calculador. Okay. All right. So let's look at the types of equations. The first type of equation that we have, for lack of a better name, I call a name equation. A name equation is basically when you give a specific name to a mathematical expression. Like if you wanted to get x to the sine of x minus e to the x's attention, and you didn't want to keep saying, hey, x to the sine of x minus e to the x. You want to go get a milkshake? X to the sine of x minus e to the x? You're like, that's a mouthful. I'm going to give you a nickname. Your new name is F. He's like, okay. So now we can just refer to him as F. Right? So that's this. Oh, there we go. This function, this expression over here has now a new name. His name is F. Now the of x, remember, is defining the independent variable, but that's a name equation. The left side is now equal to the right side. If you want to talk about the right side, you can just refer to it as F. It's kind of like in English where we have pronouns. Yes? Pronouns. Let's not get into no, just regular pronouns, right? I met up with Mr. Kilford, and then Mr. Kilford and I got a milkshake. And after that, Mr. Kilford and I went and played disc golf, and Mr. Kilford threw a disc so fast it evaporated because he has strong. Mr. Kilford I would say Mr. Kilford and I went for a milkshake, and then he, right? There you go. It's the same thing here. These are substitutes. You don't want to keep saying x to the sine of x minus e to the x. Sometimes you say f of x, f of x, f of x. That's what they're for. Economy. That's the first type of equation. Mr. Guilford can throw really fast. You stand by the makes a great sound. Yeah, exactly. I only mentioned that because it came up on one of my memories this morning. You know, my phone is an Android, but it says, "Hey, Google Drive, hey, here's from like 6 years ago." And I'm going through, and Mr. Guilford, I filmed him throwing, and then I was like, "Wow, that was 6 years ago already! Wow, time flies like a disc, you know, when it's thrown by Mr. Guilford." I just thought of that. The second type of equation is called a conditional equation, like a conditional surrender, right? Conditional equation. That is an equation that is true, but not always, but sometimes, yes. Okay. It's only true under certain conditions. And you have been conditioned to do what with those types of equations your entire mathematical career? Solve them. That's what we do. These are puzzles, right? Your job for a conditional equation is to find the conditions under which it is true. You solve, okay? Examples would be like x squared equals 6x minus 8. You have a variable there. And this could be true, but not necessarily always true. So you would then proceed to solve it and then find, I think this one has two values, 4 and 2, I believe. Maybe not. 4 and 2, 2 is 4. 4 and 2, no, 2 and 4, 4 plus minus 6 plus 8. Negative 4, 2. No, 2 and 4, something like that. Yeah, I mean, you would solve it, right? Okay, conditional equations. We're not going to be working with conditional equations. I got to solve this now. It's bothering me. X squared minus 6x plus 8, right? And then you use the quadratic formula, right? Or you try to what it? F it, right? So you got x, factors of 8 that add up to 6. 4 and 2, right? And they're both negative, right? So positive 4 and positive 2. That's what I thought. That's what I said. Yeah. Okay. Good for me. Yeah. So we solved. So yeah, thank you. This is only true when x is 4 and x is 2. That's it. Other values, it's not true, right? When will Russia attack Scandinavia? Not all the time. Only if Finland and Sweden join NATO, right? Under those conditions. Maybe. We'll see. Yeah. All right. What other types of equations do we have? Contradictions. We're making headway today, aren't we? Outside of a math classroom, where have you heard the term contradiction? When you're describing your friend? Yeah. He is a real contradiction. He says this and then he does that. And then he's allergic to milk, but he gets a milkshake. Do you want a milkshake? What does a contradiction mean? It contradicts. Very good. What's a dog? Well, it's a D-O-G. It's a dog. Let's define a word with the word. That's always good. That's how progress is made. Dog. No, what does it mean to contradict? Contra means what? Against. Contraband, right? If you don't like the Mighty Unicorn Band, you're contraband, right? I'm against the band. Down with the alma mater, right? The fight song, contraband. I'm against. So if you're a contradiction, you're against what? Dictions. I'm against dictions. Words. Thank you. Against words. So that's where it comes from. A contradiction is basically, it's like false logic, something that goes against something, right? Like it's not going to rain today, but yet there is raining. It's not raining. It's very sunny outside. Yeah, but it is raining outside, isn't it? Just not outside these two windows. It is raining. The sun ain't going to shine today. The sun is not going to shine today. It's 5 o'clock somewhere, right? Very good. No, let's talk about what it means mathematically. Remember I told you that if you use the equal sign, you better be darn sure that the left side equals the right side. Otherwise, you're whating? You're lying. A contradiction is basically a lie. It's a lying sentence, right? So it's an equation. You have an equal sign. It equates to expressions that are never equal. For example, 5 equals 7, right? Walk around with a shirt, just 5 equals 7. And you're going to start triggering people, right? Come at me, bro. 5 equals 7. Contradiction. No, it don't. Okay. No, it don't. Now that one's kind of trivial because there's no variables there, but we can also have equations like this. The square root of -1 minus x equals ln of x. No, it don't. Are there any values of x that make this true? None. So this one is non-trivial because it has variables in it. How would we know that graphically? How would, because I can graph things with x, right? If I graph this in y1 and I graph this in y2, or I graph them separately, how would I know graphically that there's no solutions? They don't touch. No touching. Yeah, we call that what? They don't what? Y'all said it. Intersect. They don't intersect. They don't intersect. So if you could draw two graphs that pass the vertical line test, one going this way, one going that way, there's no solution. They don't intersect. They don't touch. So you can write that, but you're lying, right? No solution. How would that come out algebraically? Because y'all did these in algebra too. If you think you have a conditional equation, if you're like, this is true under certain conditions, and I'm going to set out algebraically to find those values that make it true. When you get to the bottom, how would you discover that it was all for naught? There are no solutions. Graphically, they don't intersect, but algebraically, think back to algebra 2. Did your teacher not give you any contradictions? Like you had a whole homework assignment. Solve, if possible, right? A little mathematical foreshadowing. Oh, some of these can't be solved. Some of these are contradictions. Come on, help me out. Very good.
Square root of -1 minus x is not equal to the natural log.
Oh, very good. If you know there's no solution, you can come back and fix that. And you can be like, I don't think so, right? Like if someone had that graffitied on the wall, you'd like walk by and like fix it, right? And then you call yourself Banksy. But how would that come out algebraically? You simplify it. Well, you're trying to solve it. Okay, I'm going to have to like lead you to where I want you to be. Graphically, we know there's no solution because they don't what again? They don't intersect. But algebraically, if you were to do that, you would work all the way down and get something that was not true. Okay. Now remember that if you start with x's and you work all the way down and you're trying to get x by itself, if at the end you ended up with something like 5 equals 7, does your teacher tell you what to happen if your variables go away and you're left with an untrue statement? That never happened? Oh my goodness. Oh my goodness gracious.
It wasn't ingrained into.
Well, we can't really solve this one because this one is a little bit harder, but there are algebraic problems. If you were working down and you had x's up here and then the x's canceled out, like you had x equals and the x like x plus 5 and x minus 7, right? If you were to continue, what would you do? You have x plus 5 and x minus, let's do x plus 5 and x plus 7. Well, you would subtract x from both sides, right? And you get 5 equals 7. And you're like, what do I do now, teacher? The x's went bye-bye. Well, when you get something like this, we usually write this. We put 2 ramming arrows. That is the mathematical symbol for contradiction. And it means how many solutions does that conditional equation that you thought was conditional have? No solutions, right? You never had an answer of no solutions in your algebra 2 class? Holy moly. Well, y'all were doing it during the pandemic, right? And we were looking for solutions. We didn't want to encourage the no solution. You should have. Look, it's starting to come back. It's starting to come back. We're peeling back some of the layers. You might have buried it deep, right? Because it was a traumatic time. right? We're zooming, right? If you work down algebraically and the variables disappear and you end up with an untrue statement, then it's a contradiction. The original equality was actually a lie, and you can fix it by saying not equal, or you can just answer the question, contradiction, no solution, and move on, right? And not let it bother you. Just move on. Bury the hatchet, they say. Bury the hatchet. That means to let things rest, right? Bury the hatchet. But
Already used it. You need to hide the evidence.
right. Now there's a song by Ice Nine Kills off one of their early albums called Bury the Hatchet in Your Face. Now that just kind of goes against the whole meaning of what bury the hatchet means, right? That's like, no, you're taking that the wrong way, bro.
And then you bury it.
You should go home and sleep like a baby. Right? What do you want me to do?
Wake up crying in the middle of the night until somebody else.
I know, with poop in your pants, right? Amber Heard, right? They're calling her Amber Turd now. Is that fair? I don't know. Now, let's look at this last one here. The last type of equation is called an identity. An identity. Do you have an identity, Tyler?
Maybe.
Maybe. That's a great answer. You're still in the formative years of your life. You're developing an identity, perhaps. Do you have an identity, Chris?
At least 34.
Do you have a mirror at home? What do you see when you look in the mirror? You see yourself. It's backwards, right? Everything's flipped. Do you know that you can actually make it not backwards? It's pretty cool. If you get two mirrors and you put them together at a right angle, and then you look at them this way, here's your eyes. I'm not really good with eyes, but you look, here's your nose, here's your head, and then you look this way, they'll reflect off each other and you won't be backwards anymore. So it's a little trick. But anyway, when you look in the mirror, what do you see? You see yourself. That's your identity. It's me. I'm here and I'm also there. And the mirror is like the equal sign, right? You have me, and then you have the mirror, and then you have me, right? The mirror is the equal sign. Do you equal you? I sure hope so. Okay. That's your identity. That's who you are. So that's kind of why we use the word identity.
You are the.
Here we go. Mathematically, an identity is an equation that, of course, again, equates two expressions, but they are true, not just some of the times for random values of X or under certain conditions. They're true for all values that are in the domain. So what that means is if it's a variable and you plug it into the left side and you plug that same number into the right side, if it's not like division by zero, if it computes to a number, it's always going to be the same number on the left and the right side. Now, here's a trivial identity, right? 4 equals 4. That's an identity, right? Here's another one. 4 squared is 16. That's an identity. All right? Here's another one. This is really important one. The square root of x squared is the same as the absolute value of x. Now, that's a non-trivial one. These are kind of trivial because they're really the same thing. Now, when might you want to use an identity? This one is not so useful. 4 equals 4. But maybe 4 squared equals 16 is useful, right? If you're working with the 16, remember earlier in the year we had exponentials, right? And I said you could get the bases the same, then you could set the exponents equal to each other. It might be better to replace the 16 parentheses with a 4 squared. So having a different version of the same thing is kind of nice, right? A different version of the same thing is kind of nice. It's kind of like a whole bunch of ramen noodles, but the only difference is the awesome little flavor packet that makes them all the same but different. That's a horrible analogy. Never mind. Never mind.
It's like the milkshakes.
Yeah, these are actually the same. Substitute one for the other, everything's good. Now, this one over here with the x is very important because in calculus, we might prefer, instead of working with the absolute value of x, which basically makes a number positive, right? If it's negative, break off the negative. If it's positive, just leave it as is. We might like to write it as the square root of x squared, the unsimplified version, because they accomplish the same thing, right? The absolute value of x makes the number positive by breaking off any negative that might be there, right? Maybe cutting it off with a hatchet. But this one does it a different way. Like a computer program says, all right, I'm going to do the same thing. I'm just going to do it differently. I'm going to square the number, which now might get rid of any negative that might be there. Now, granted, it's going to be a bigger number. So guess what I'm going to do? I'm going to take my hatchet. I'm going to cut it right back down to size. Boom. Square it first, then take the square root of it. Same thing. If you graph them, they would look the same. Now, is that also the same as the square root of x squared? Does the order matter? For functions, it does. For operations, not necessarily, but this one is not good. This one would be a conditional equation. It's not true for all x's because this one doesn't allow negative numbers, right? The whole purpose of the absolute value is to make a negative number positive so you can get a distance. This one doesn't even allow negative numbers, right? Plug in a -4 here and you're like, square root of -4. I'm in imaginary land. I'm stuck. But over here, it's like, we got you. -4 squared, you're 16. Now the square root of 16 is 4. Perfect. Okay. An identity. An identity is true for all values of x in the domain. When you have two equations that are true for all values in the domain, that is, if you have an identity, these become mathematical synonyms for each other. Mathematical synonyms. So what you're going to be learning in this section is I'm going to be providing you entries into your mathematical thesaurus. Thesaurus. Thesaurus was the smartest dinosaur that ever lived. Of course, he's still extinct, but he had quite the vocabulary. That's why he's called the thesaurus. They've unearthed a couple of thesaurus bones, you know, like bronze, yeah. And there's always like a giant pair of eyeglasses, like the one Colin's wearing, found with the bones. And that's how they can identify it as the thesaurus. Because it was like Asia, right? No. The thesaurus wore glasses because really, people who wear glasses naturally smarter, right? That's at least that was the stereotype back in 66, was it million years ago? $44 billion, 66 million years ago.
He was so smart, he pronounced it
Thesaurus. There you go. You're good with those little word plays there. I prefer thesaurus, the one and the only thesaurus. So we've been pronouncing it wrong this whole time. We call the book a thesaurus because of the dinosaur who had quite the vocabulary, but this whole time it should have been called thesaurus. Man, we're learning so many good things. Synonyms. All right, so here's your first set of identities. The reciprocal identities. You need to know the category. The reciprocal identities. And you know what? You already know these. You already know these. Here's the first one. Sine of an angle theta is equal to 1 over cosecant of theta for all values of theta that work. Now, all values of theta work on the left, but remember, cosecant is undefined at multiples of pi. So for all the other values that aren't multiples of pi, plug it into the left, plug it into the right, same. Now, did we already know that? Did we already know that sine was 1 over cosecant? We did, because sine equals 1 over cosecant just means that cosecant is what? 1 over sine. And if we had to find the cosecant from the unit circle, like if I asked you what is cosecant of pi 6, how would you find cosecant of pi 6? No. What is the, we should have a pop quiz. What is the cosecant of pi 6? 2. Thank you, Brady. It's 2 because it's the reciprocal of the y value, and the y value is the sine value. Is there a way to remember that y and sine and height are related? Sine, y, height. So when you flip the y, you get the cosecant. Well, that's what this means. Cosecant of pi 6 is 1 over sine of pi 6. Well, what is sine of pi 6? It's 1/2. Now what's 1 over 1/2? Stay, change, flip. And 1 times 2 over 1 is 2 over 1, which is 2. Hey, it works. Now, that's a lot of work right there. This is nothing more than formalizing what we already know. Sine and cosecant are reciprocals of each other. So if you have a sine, you can replace it with a 1 over cosecant. If you have a cosecant, you can replace it with a 1 over sine. They are mathematical synonyms with each other, right? Like I was sitting in my room deciding whether I should go to prom, and I was looking for a sine. You could say I was sitting in my room deciding whether to go to prom, and I was looking for a 1 over cosecant. And people will be like, oh, I got you. I got you. You're looking for a sine because it's a synonym. Sine is 1 over cosecant. Mix that up in your writing. See how your English teacher likes it. Hey, what's the reciprocal of cosine? Secant. So without looking, cosine is equal to what in the reciprocal identity family? 1 over secant. Very good. And secant without looking is 1 over what? 1 over, I should look, right, is 1 over cosine, right? 1 over cosine. Good, good. Now, once these are identities and you know they're true, and we'll prove it here in a second, you can actually start manipulating them. Like if I wanted to multiply like a conditional equation, if I wanted to multiply both sides times secant, since it's an identity, I could do that. These would divide out, and I ended up with secant times cosine is 1. Hey, that's another identity. You want to memorize that one? What's secant times cosine? 1. Okay, you want to memorize that? What's another name for 1? Secant times cosine, right? So we're doing the cheer. We're number 1. Again, we're number 1. Who are we? We're number secant times cosine. People are like, yeah, we are. You want to memorize that? No, because the commutative property says that what's cosine times secant? It's also 1. Do you want to memorize that? No, you don't need to, because if you know fundamentally that cosine and secant are reciprocals of each other, you not only know that cosine is 1 over secant and secant is 1 over cosine, what's anything times its reciprocal? What's 5 times the 5th? 1. What's e times 1 over e? 1. What's 2/3 times 3/2? 1. Anything times its reciprocal is what? 1. So guess what tangent times cotangent is? 1. And why does that work? Tangent and cotangents are what of each other? Reciprocals. There's the last pair of reciprocal identities. Tangent is 1 over cotangent, and cotangent is 1 over tangent. Do you already know these coming in? You already know these? You already know these. This is how we got the other 4 trig functions from the unit circle. The only difference is we are formally stating them now. Instead of x, in terms of x, y, and r, we're stating them as full-fledged identities. Okay, now let me show you. Here's a little taste of the proof. Because these are fundamental identities, they're like the bottom rung. They're the most basic. They're the building blocks of other identities. If we want to prove that it's true, we have to go like molecular level here. We have to like go to the DNA of these trig functions, which means we have to go to their definitions in terms of x, y, and r. So I'm going to prove to you that tangent is 1 over cotangent. Okay, I'm going to prove to you. Now, is it raining outside? How do you know it's not raining outside? Well, let me see. Hang on. I'm going to come over here. It is not raining outside of this window. Therefore, it's not raining outside. Oh, I better check more than just one window. Silly me. Let me check another window. Ah, it is not raining outside of this window also as well. Therefore, outside of 2 windows, it is not raining. Therefore, it must not be raining outside. I better go check Mrs. Lincoln's room. I wonder if it's raining outside her classroom. What if I went around and I checked all the windows in the school and was like, nope, not raining outside any windows. Therefore, it must not be raining outside. Would that be true necessarily? No, that's not true. It was like pouring rain yesterday morning at 6 a.m. in my house. My wife left to go to work. I called her when she called me when she got to work. I said, wow, you got there safely in the rain. I'm proud of you. She goes, actually, when I got to Herbert's Taco, the rain just stopped. And it was clear the rest of the way was dry. And I was like, but I thought it was raining outside. She goes, it was at our house, but not. And I'm like, how is that possible? If it's not raining outside of 1,000 windows, that doesn't mean it's not raining outside. Inconceivable. It's raining somewhere. It's 5 o'clock somewhere, right? So when you check individual cases, mathematically, that's called verification. You're just verifying, right? I'm verifying one window at a time. If you verified for the rest of your life, you made pilgrimages to windows and you just looked outside to see if there was raining. If you happen to get lucky and every window you checked for the rest of your pathetic life, there was no rain outside that window, could you then on your dying bed say, it was not raining outside, and be taken seriously? No, I was like, dude, literally as you said that, I got a weather report. It's raining in China. Cats and dogs, actually. Yeah. Let's hope that that they don't have COVID. Let's hope that, it all started with a bat, right? No, that would be pointless, because here's the deal. No amount of verification constitutes a proof. No amount of verification constitutes proof. So how do we prove something mathematically? How do we prove that something is true all the time if we can't verify infinitely many cases? How do we do it? Very good, with math. You don't. You just like take it on faith. I guess it's not raining. Never was. Never will be. Will the sun come up tomorrow? It's come up every morning since I've been alive. Ask the dinosaurs. If the sun comes up and the dinosaur's not there, did the sun actually rise? The answer to that question is we're going to use variables. If you can manipulate something using variables and show that it's true with variables, then on the back end, you could say, aha, all along the way, those variables could have been what? Anything. So let me show you real quickly here. We're going to prove something by first drawing a line down the middle. We are now going to treat these two things separately as separate expressions, and I want to manipulate one into the other. The first strategy is to start on the side that has more information, that looks more complicated, because I'll tell you this, in life, it's so much easier to tear something down than it is to build it up, right? Is that necessarily what we want to do with people? Tear them down so we can build them up? It's easier to tear something down. I built homes for 3 years before I started teaching. I was able to build homes in 77 days, but it took a lot of help, took a lot of know-how. But we had a home that went burned. It burned in Braun Oaks subdivision overnight. The house burned down. And I hired somebody. He came in with just a bulldozer and he destroyed it. He took it down one day. It had taken like 60 days to get to that point. Is it easier to tear something down or build something up? Tear it down. So we're going to start on the side that has more information, which is the right side. It has more information. And what we're going to do is we're going to tear it down until it looks like tangent of theta. And then we're going to be like, ah, I knew it. I knew it. They were the same all along. And then we're going to celebrate by saying ole at the end or something like that. I guess we'll have to wait for tomorrow. But at least we learned a lot today, right? Happy birthday, Liz. No, seriously, look up Harry Styles singing, what is it, Juice? Is that what the song's called? Yeah, look up Harry Styles singing Juice. You won't regret it. Hey, you Styles. Have a good day. I will. You too, Brady.